Let's see. So I'll just go through some of the work that I was like doing for the last 4 or 5 years and see how like we can like what the parts that you find interesting, and then we can discuss more on those. Yeah, so the initial part, of course, started out with just learning some things, and that like the first thing that when I came in contact with quantum is like this Coursera course from Umesh Vazirani. So that was in 2012. And then for a few years, I was working in India in something absolutely different, nothing quantum in it, mostly like satellite designing, like programming satellites. And perhaps the only thing that is common with that 3 years of working and today is I'm still at the assembly level. So you program mostly satellites with assembly, and quantum computers are still programming in assembly level. And then I was doing my master's in TU Delft, and of course there are these wonderful courses from TU Delft that gets you started on all the different fields of quantum computing. But yeah, that's not the thing that I'm going to talk about mostly. I'll be talking about the projects that I was doing. The first project that I started out during my master thesis with Carmina, Kuhn, and Zaid is trying to find quantum algorithms for DNA sequencing. That also kind of continued in the first year of my PhD, where I was looking at other different forms of this DNA sequencing using the more recent algorithms, like from the NISQ era, QAOA mostly. Thereafter, like after this first year of my PhD, I moved away a little bit from genomics, and I'll tell you about the reasons for that, but more towards algorithmic information theory and what are the different quantum algorithms that you can apply for it. And eventually in the last year, I found like one of the best things that you can actually do with algorithmic information theory is to make reinforcement learning agents. So currently I'm basically trying to find the synergy between reinforcement learning and quantum information processing. Yeah, so that's how kind of my interest shifted from quantum computing to accelerate genomics to quantum computing to model algorithmic information theory. And then from algorithm, like you can also think of it the other way around. Algorithmic information theory can also be used to model quantum computation in general. So the first idea that was like, let's say in 2016, is that you can build an universal quantum computer. Like that's possible to do. That's what most researchers in our field was like trying to do at that time, trying to build a fault-tolerant quantum computer. But also we realized that while it's possible to do, it's not going to be applied for all possible algorithms. So that's where the idea of accelerators come in, that you want to apply it to very specific problems. And what can those problems that can give you quantum advantage? Of course, you have to pick one, and I picked genomics just because I'm also interested in how life works and those kind of things, like digital data and life. Now you can apply quantum, like there are different classical algorithms. You have to choose one and then try to see if you can accelerate that on quantum computation. And that's called as like DNA sequence reconstruction. Happens to be a very tough problem for classical supercomputers even. And that's basically what I attempted to do for my master thesis. So that's like the first part. The second, like when I started my PhD research, like when I was doing my master's, actually it was in 2016 to 17, and that's the year that Preskel gave his lecture. Or in 2014 is when QAOA and VQE was published. So at that time it wasn't really popular. The NISQ era of algorithm design wasn't in. But when I started my PhD, by that time, pretty much everybody was looking at QAOA and VQE. So like I thought, why not give that a try? And that turned out to be more suitable for another different type of DNA sequence reconstruction. Yeah, so that's basically what I was working on, and the publications were on those kind of different quantum algorithms. The major learning, again, from this kind of working with DNA data is the current NISQ era or the NISQ simulators. You always have this limit of this 50 qubit barrier, either way around, like whether you're working with real hardware or simulators. And if you really want to show really appreciate the algorithm design, you need to work on something that requires much less number of qubits, even for the smallest proof of concept, basically. So I found that sequence analysis might be something of that. Also, like we were talking with some genomics experts, and they said that by the time that quantum computers are going to reach this fault tolerant era, these might not be the most pressing problems. So we need to look at the things that will be problems 10 years down the line. And sequence analysis probably is one of them. So that's where I kind of started learning about algorithmic information theory, because like if you look at the smallest proof of concept of sequence analysis, it's very related to some problems in algorithmic information theory. It's called metabiology, where you're not working with real DNA sequences, but looking at all the entire space of possible small DNA sequences and what properties they may have. Like, can they self-replicate, for example? That's like a very important property of life. So what kind of sequences can replicate itself when run on a computer? Yeah, so those were like the publications on that. And while working on that, I also was working on quantum Turing machines. So that's like what David Deutsch first proposed in 1990s. But that's what he proposed was quantum Turing machine. And we know that there is an universal form of it, the universal Turing machine. So there should also be a quantum universal Turing machine. So that's the model that we propose, that within the Turing machine, you don't really have to change the program. You can also encode a superposition of programs as well as your superposition of data, so that you can like truly have a quantum version of the universal Turing machine. That's not only programmable, but it can be there can be multiple programs running in superposition in that model of computation. So that's again can be applied for these kind of genomics problems. So that's basically what I was still pretty much in genomics. But then I was looking at other applications where this model can be used for, and that was AGI, or artificial general intelligence. So that's like the kind of intelligence where you have just one core algorithm and you keep improving on it, give it a lot of computation power, and it tries to eventually learn everything. It's like a very fictitious thing. But there are also very rigorous theoretical models in classical computation called XE from Marcus Hutter. And they try to prove that given enough computational resources, asymptotically, it can learn any environments, classical environments. So like that's basically what I'm trying to do now, extend this XE model for quantum environments, and things start to get a bit different in quantum, of course, because you cannot, like, even if you have full knowledge of a quantum system, you cannot predict the exact next observation, because if you know that's a Hadamard gate, and if you're measuring in the Z basis, you know the distribution of zeros and ones, but you cannot exactly predict the next one. So that needs to be taken into account within the agent model, the formalism. And that's also kind of was inspired by some work done by IQOQI in Vienna. And these guys were working on formulating quantum mechanics purely based on algorithmic information theory. But the problem that they had is they were using like passive algorithmic information theory. They were like, I was trying to extend it to the active version of it, where the agent also has some choice. And in any quantum experiments, we as experimenters also have a choice of which measurement basis do we measure in. And that also needs to be taken into account in the learning task. And so the rest is like the different plans that I have for the next year, but I'm not sure which way it will go. So quickly, the major learnings. Quantum genome sequencing was not really studied before when I was starting out with. And the first doubt I had, of course, was maybe like some of the other, like my colleagues over here, they might be having the same doubt that why hasn't it been studied before? Is it because it's like not advantageous? And that's something that happens a lot in this field, mostly because it's too new a field, and just the simple reason is that nobody has looked at it. And you might be the first one to get that idea that why not try this for this particular problem? So that's kind of what happened with genome sequencing as well. There was one research from 2000, so that's like 20 years back, and then there's nothing. So we found out that yes, there are advantages and there's possible. So these are the two different algorithms that you can look at. So the first one I looked during my master thesis, and the second one I looked during the first year of my PhD. So the first one was basically based on some improvements of Groover search using the idea of associative memory. The second one was basically solving a Hamiltonian cycle using QAOA, using traveling salesman problem and QAOA. So for both of these problems, it's like it's quite easy to appreciate that you cannot scale up and test a huge proof of concept right now. For the first problem, we could go up to DNA sequences of length 16. So that already requires some kind of like around 32 qubits. And for the second one, we could go up to reads of 4. That already requires 16 qubits. And the next one requires square of 5, so 25 qubits. And D-Wave already can't do a very good embedding on 25 qubits. And also like the limitations was also from OpenQL and QX. And if you just try to initialize a 25 qubit register and tell that they are going to do this kind of operations on it, it already kind of crashes with the memory on a normal laptop, for example. But the main reason is like the main thing is the scaling up. You can go up to 5 reads, but that's not going to take you any near to real world problems. You really need to go to 50 reads or something like that for real world problems. Yeah, so now for the next problem, I had this learnings that I need to choose a problem and work on it that has these kind of features in it. And quantum genome sequence analysis was that problem that I found might be good enough, because you can make an universal Turing machine, quantum universal Turing machine, with around 32 qubits, I guess, if I remember it exactly. So the idea is this is how a normal classical Turing machine looks like, and this is how the quantum Turing machine looks like, where the Yangians are basically the qubits. And the model that David Deutsch proposed how you write a half adder code, for example, but your data can be in a superposition. I kind of try to make both in a superposition, and that changes a lot of the quantum circuit blocks and how you need to do that. So that allows you to actually inspect some of this algorithmic information theory metrics. And now you might be wondering what's that useful for. So this was more like how the circuits look like. Each of those small blocks again expands to this huge blocks of gates. And we could show it for a very simple Turing machine that the results are as expected, but that's not the fun part. The fun part is when you have this model of Turing machine, and instead of the binary alphabet, you put the DNA sequence. So you basically have a 2-qubit encoding of the DNAs in it, and then you can sample of some specific properties of this DNA sequences. For example, this is an interaction graph between the coronavirus proteins and the human proteins. The red are the human ones. The red are the coronavirus ones, and the black dots are the human ones. And it shows that which protein interacts with which human protein, and that's kind of is what's useful for building these vaccines. And there's a group that uses entirely classical algorithm. I'm not claiming to do anything with quantum over here, but they show that this interaction graphs can entirely be derived from the protein sequences and how much they are close in this algorithmic complexity, like how these sequences are close. So if they are close, they interact. If they are very far off in complexity, they don't. And these are the kind of things where these kind of quantum Turing machine models can be applied to. Of course, you don't have enough qubits to them right now. Yeah, so the last thing that I've been working for the last 1 year is just to look at the inverse problem using algorithmic information theory to model quantum computation. And the reason is uh, algorithmic information theory is computationally perhaps more difficult than quantum information, mostly because quantum Turing machines are still Turing degree in the same Turing degree as classical computers. So even BQP, QMA, they are still within the polynomial hierarchy. But algorithmic information theory lets you go way beyond it. Like they lets you deal with uncomputable problems, so to say, like the halting problem, those kind of things. So they are basically super Turing oracles in there. And but like if you are always working with super Turing things and not really that takes you way away from practical stuffs. So that's the good feature of AIT, that there are some approximation that people have come up with, and those can really reveal a lot about data, much more than maybe what black box neural networks can do. So they are really good for making causal models and causal discovery. So this formalism of AIT is also almost as fundamental or general as quantum information theory. And you can argue in many ways that the shortest program, I mean, people have already worked on it, that the shortest program also tells you the geodesic distance and the Lagrangian action in a specific type of space. So there is a lot of correspondence between optimizing a compiler, for example, finding the shortest program, and what actually happens when a rock rolls down a hill or something. So the basic idea is, given a sequence, what's the next thing that you would predict, and for that, and that's how pretty much we build every single model in the world. Like the sun rises every day, so you plan to see a sunrise tomorrow and not some other planet at the same place. And that's pretty much given by the shortest program that you can write. So the shortest program that gives you that outputs this continuation of the sequence is the most likely to happen. So that is what algorithmic information theory is all about. And this is kind of the cartoon of, like, you want to minimize your assumptions, and that's the way that we do science and for in general scientific modeling. So things change a bit in quantum computing because of the participatory observer effect, which says that you need to choose the measurement basis, and basically the observer, you can argue it in this way, that the observer kind of kills the cat or makes the cat alive. So as long as the observer is not looking, there is no state. So to do this, you need to use reinforcement learning, right? So you need to have an agent outside the system. You need to look at two different stuffs: the environment, the quantum environment, and the agent. Fortunately, there is already such a model in classical computer where you have the agent and the environment as two different Turing machines interacting with each other. So I was trying to extend this formalism in the quantum domain. So this is what I'm working on currently, like as we speak, in the last few months. So this is like the formal equation of our model. That's, again, not the most important. This is basically the summary of what I'm working on right now. I call it the quantum knowledge seeking agent because, like, there's already things called as classical knowledge seeking agents that try to not receive rewards from the environment, but try to model the environment as best as possible. So in this case, we are trying to model a quantum environment. And yeah, so this basically a quantum process, which can be open process. So it can, like, you can lose information out of it. You can have measurements within it. You might not be measuring all the qubits in the circuit. You might have access to only a subsystem of it. So you have all these different cases that you can work with. And you try to optimize the tomography algorithm within it. And that's basically what the agent tries to do using the shortest Turing machine code. And then over on top of this agent model, there is evolutionary algorithm. So that tries to optimize the computational resources needed to do that process tomography. So mostly in algorithmic information theory, we consider only the length of the program. But again, you can trade off the length of the program with other metrics, energy, how much approximation you want, what's the classical memory that you need to store the previous measurement results, how much time your short code takes. And again, this is from classical computing that we know that often the shortest length of the code is not the most preferred one. Like a recursive algorithm looks really nice, but it takes a lot of time, a lot of memory to run actually. So it's always a trade-off between these parameters, and sometimes that would affect what model you get out of the system. So if it's like you are looking at a very small type of problems, Newtonian physics or classical mechanics might be enough. But if you're trying to do something like a time travel or something like, not time travel, but yeah, like you're moving very close to the speed of light, then you need this relativistic theory. And then you have this extra parameter that you might just prune off if you're doing, if you're only trying to make a classical model for it. Yeah, so that's this is like the last slide where I also have some list of other things that I plan to go into in the future, but yeah, there has to be some good synergy between what I'm doing right now and what these would require me to do. For example, like I find a lot of synergy with maths work in quantum information, but then again, we need to figure out how we can collaborate on some of these things, for example. The basic idea for me is I have the space of all possible things that can happen, and then there is a much smaller subspace within it that are valid transformations given the set of computer programs that you have. And again, within that box, you have another smaller box of how many of those transformations are really useful for real world problems. So it's all about trying to figure out the subspace within this entire space of possible transformations. Yeah, so that's more or less a summary of what I've been doing. Thank you.
Impressive. How many persons are you?
Second. Yeah. So yeah, that was kind of a summary of. I've been doing a lot of different things, mostly because of these things that you learn when you start to do quantum algorithms that cannot go too deep and have a lot of heuristics within your within specific applications. You just reach the limit of qubits. So then you might want to take that same algorithm and see where else you can apply.
Yeah. Yeah, great. Here regarding self-replication, I don't know if you talked with Thomas Gabor from Munich. We had a look at goals for self-replication of neural networks. That I mean, it's completely useless, but we try to learn neural networks that are able to replicate themselves to find
really
some
nice.
fixed points. I can give you the pointer for that. So again, it's completely senseless. You can do nothing with it. But from a theoretically point of view, it's quite nice that they are able to learn their own fixed points. And we called it the spaghetti paper because it was just yeah, a lot of spaghettis in this paper. And
nice.
what also, I can give you the link. And what I also thought about was, it was with a student, we tried to have a look if we can make the game of life, a probabilistic game of life on a quantum annealer. And yeah, it was fun, and it worked. Yeah. Yeah. And years ago, I like this, like when you said, hey, I would like to have a general AI, but not one that works in a classical environment, but in a quantum environment. This is what I understood. This is, I mean, heavy. The general AI is the topic, and you expand then the environment from classical to quantum. So chapeau, really nice. I like the idea. And I thought about what we did was we tried to learn physics. We tried to learn gravity. I don't know if it pitched this to you or to some other person. We had some simulation with some balls of different structure, and we had a simulation where we threw the balls, and we tried to learn the direction of the bouncing balls.
Wow! Yeah.
So inherent rules given in that, some kind of physics basically.
Yeah.
And then lastly, we here with this swarm intelligence, because on your last slide there was the word swarm intelligence. We came from the economics. So inherent swarm behavior in the financial markets, and we try to model this using multi-agent reinforcement learning, but also using fish swarms.
Okay, yeah. So like actually I was working on swarm intelligence before I came to Tudor. So that was always a soft corner for me.
Yeah.
But then you find that quantum mechanics is inherently a two-person theory. So you have one observer and one system. The moment you introduce a third observer, everything breaks down. You have all these paradoxes come up. And I was like thinking, why not use swarm intelligence? And there is some work called classical coarse graining of quantum information, where you can have swarm systems, classical swarm systems looking at a quantum system and still come up with what's happening in the quantum world based on partial observations.
Yeah. Wow. Okay. And I mean, you left the title of your PhD open, but what is your current working title?
It's.
I mean, it could be like super super interesting topics from today.
Quantum algorithms for algorithmic information, then applied to genomics and artificial intelligence, something like that. But yeah, it keeps changing every month, so I just skipped it.
Great. Yeah. Really looks good.
Okay. Sorry. Thank you for your presentation. I have to
Thank
go.
you. Yeah. Sure. Yeah.
I see you around.
Yeah.
See you. Bye.
See you. Bye.
Okay. Yeah, nice overview. So I think in the next days and weeks we can chat and talk about that. So thank you very much for this. Presenting, and then we now can approach you and we know what topics you're thinking about.
Yeah.
That's really nice. Okay, cool. Any other questions from the others? Yeah.
Can we upload the recording on Teams?
Yeah, I think it will be automatically there. You mean in the folder or something, or?
Yeah, just to have it to access it somehow. It doesn't matter.
Yeah, we'll have a look how this works. So yeah, sure, let's do that. Okay. Yeah, then see you around. Yeah, then see you next week, and yeah, nothing more to say. Okay.
See you.
See you. Bye.
Bye.